Alright, let's go. Number 8. The Tabletop Casimir-Effect Dimension Tests. Ricardo Decca and his colleagues at Indiana University, Purdue University, Indianapolis were not hunting extra dimensions when they built their apparatus in the mid-2000s. They were trying to measure the Casimir-force, the tiny attractive pull between two uncharged metal plates held only microns apart, predicted by the Dutch physicist Hendrik Casimir in a 1948 paper as a quirk of quantum vacuum fluctuations. It was a precision measurement problem, not a cosmology project. Standard three-dimensional physics predicts the Casimir-force with extraordinary precision. If gravity, or any other force, leaked into hidden compact dimensions at submicron scales, the measured force between the plates should deviate from the standard prediction, even by a fraction of a percent. That fraction would be the fingerprint of a fifth direction. They found nothing. The force matched the four-dimensional prediction. Not approximately. Exactly. No deviation, no leak, no door. Decca's team, publishing in Physical Review D in 2007 and refining in Physical Review Letters in 2016, ruled out Yukawa-type deviations from Newtonian gravity at separations between roughly 40 nanometers and 8 micrometers. Their limits tighten prior bounds by more than an order of magnitude in the submicron regime, the exact regime the earliest large extra-dimension models had lived in. Theorists proposed the dimensions were smaller than the resolution. Decca extended the measurement range. They proposed the leak was chiral. Spin-dependent tests followed. They proposed the compactification radius was tuned to hide inside experimental error. Tighter error bars killed that. They proposed only certain particle species felt the extra dimensions, but the Casimir force involves the entire quantum vacuum. Every escape hatch closed one by one. The plates gave nothing back. The vacuum between two plates, the width of a red blood cell, is behaving exactly as if reality has three spatial dimensions and no others. Whatever else is hiding out there, it is not hiding at that scale. If dimensions do not leak into the space between two plates on a tabletop, where exactly are they leaking? The plates are only the beginning of where physicists have looked. Number 7. The Kaluza-Klein particle searches. Theodore Kaluza was a mathematics lecturer in Königsberg, trying to unify Einstein's brand new general relativity with Maxwell's electromagnetism. In 1919, he mailed a paper to Einstein, proposing that both forces might drop out of a single equation if space had 5 dimensions instead of 4. Einstein sat on the manuscript for 2 years before agreeing to submit it to the Prussian Academy. Kaluza's paper, published in 1921 in the Proceedings of the Prussian Academy of Sciences, and refined by the Swedish physicist Oskar Klein in a 1926 paper in Zeitschrift für Physik, made a concrete prediction. If the extra dimension existed but was curled into a tiny loop, any particle traveling through it would appear to us as a heavier version of itself. Every known particle should possess an infinite tower of massive copies, Kaluza-Klein excitations, nearly a century of searching. 0 towers found, not one heavy photon, not one heavy electron. The staircase Kaluza described does not appear in any detector humans have built. The Atlas collaboration, in a search published in the Journal of High Energy Physics in 2019, ruled out Kaluza-Klein gluon states below approximately 4.1 tera-electron volts. CMS pushed the limits on Kaluza-Klein graviton excitations above roughly 2.3 tera-electron volts in Physical Review D the same year. Every subsequent LHC run has extended these bounds without producing a candidate. Theorists said the extra dimension was smaller than we thought. Searches at higher energy pushed the bound further with no signal. They said only certain fields propagated through it. Models were reworked, still nothing. They said the excitation masses were suppressed by warping. Randall-Sundrum flavored searches came up empty too. They said the compactification hid the lowest excitations, but those hidden states have specific decay signatures, none of which have ever been seen in any detector. A theory Einstein reviewed personally, that a century of physicists have kept alive because the mathematics is too beautiful to discard, has produced no experimental confirmation in any collider ever built. The staircase is either far higher than we can climb, or it is not there. How long do you continue searching for a particle predicted by a theory that has never once been confirmed? Colliders are not the only tools that have come up empty. Number 6. The IceCube neutrino-based dimension search. The IceCube Neutrino Observatory, a cubic kilometer of instrumented Antarctic ice, buried roughly 2 kilometers below the South Pole surface, was built primarily to identify astrophysical sources of ultra-high-energy neutrinos. Detecting extra dimensions was a secondary use of the same data. One theorists proposed after the detector was already running and taking measurements around the clock. Certain extra-dimensional models, particularly those involving sterile neutrinos that propagate into a hidden dimension, predict a distortion in the oscillation pattern of atmospheric neutrinos as they travel through the Earth. The standard three-flavor oscillation model, worked out over decades, predicts a specific spectrum. Extra-dimensional leakage would bend that spectrum in a characteristic and unmistakable way. The IceCube collaboration analyzed years of atmospheric neutrino data. The oscillation pattern matched the standard three-dimensional prediction. No bend, no distortion, no leak. In an analysis published in Physical Review D in 2022, the IceCube collaboration reported constraints on the size of a large extra dimension coupled to sterile neutrinos, ruling out compactification radii above approximately 1 micrometer across a wide sterile neutrino mass range. The constraint improved on prior bounds by roughly an order of magnitude and pushed the surviving parameter space toward theoretical irrelevance. Model builders adjusted the sterile neutrino mass scale. The constraint tightened further with more data. They proposed the coupling to the extra dimension was suppressed. That pushed the model into experimentally uninteresting territory. They proposed a chiral coupling that IceCube's geometry could not detect, but complementary reactor experiments closed that window. They proposed the leak only affected certain flavor eigenstates. The IceCube analysis was flavor agnostic and would have seen the effect anyway. Neutrinos, the least social particles in the universe, will pass through your body at a rate of roughly 100 trillion per second while you read this sentence. If any of them are dipping into a hidden dimension along the way, that dimension is smaller than a single bacterium. What is the smallest dimension you would still believe in if no experiment could ever see it? The neutrino silence extended into gravity itself. Number 5. The Randall-Sundrum warped dimension tests. Lisa Randall at Princeton and Randall-Sundrum at Boston University were not trying to explain everything. In 1999, they were trying to solve the hierarchy problem, the mystery of why gravity is roughly 10 to the 39th times weaker than the other fundamental forces. Their answer was structural. Our universe might be a three-dimensional membrane floating in a five-dimensional warped space, and gravity might be strong somewhere else and merely dripping onto our sheet. Their model, published in Physical Review Letters in 1999 in a paper titled Large Mass Hierarchy from a Small Extra Dimension, made specific and testable predictions. Warped Kaluza-Klein gravitons should appear as resonances in particle collisions, narrow spikes in the invariant mass spectrum of dilepton and diphoton events at the LHC. The masses and couplings were calculable. The signatures were unmistakable. The LHC has been looking since the mid-2010s. The spectra are smooth, no spikes, no warping, no echo of a fifth dimension. Atlas, in a search published in Physics Letters B in 2020, excluded Randall-Sundrum gravitons below approximately 4.5 teraelectron volts for the coupling range most theorists considered natural. CMS reached comparable bounds in a Physical Review D paper the same year. The window in which the model solves the hierarchy problem it was invented to solve has been almost entirely eliminated. The graviton mass was pushed above LHC reach. The model became untestable, which is the physicist's polite word for dead. The coupling was made weaker. That reintroduced the hierarchy problem the model was designed to solve. The warping profile was adjusted. The adjustment demanded fine-tuning worse than the problem it was fixing. Additional brains were added. Each addition created new problems and solved none of the old ones. A model built to explain why the gravity holding your feet to the floor is so absurdly weaker than the electromagnetism holding the atoms in your feet together has, so far, made no prediction that has ever come true in a working detector. If gravity is leaking out of our universe, and we cannot find where it is going, is it still leaking? The problem is not confined to the LHC. Number 4. The LIGO gravitational wave test of extra-dimensional leakage. Chris Pardo, Maya Fischbach, Daniel Holds, and David Spergel were not trying to disprove extra dimensions. In 2018, they were interested in what LIGO's gravitational wave observations could tell us about the large-scale structure of space-time itself, using the famous black hole merger GW150914 as a cosmological distance ruler. If gravity leaks into extra dimensions, then gravitational waves, which are ripples in spacetime, should also leak. The intensity of a gravitational wave from a distant source should fall off faster than the inverse square law predicts, because some of its energy is being drained into hidden dimensions during the journey. The more dimensions, the steeper the drop-off. The signature was clean and calculable. The signal from GW150914, first detected on September 14, 2015, arrived at exactly the strength that four-dimensional general relativity predicts. Not fainter, not distorted, standard. Pardo, Fischbach, Holtz, and Spergel published their analysis in the Journal of Cosmology and Astroparticle Physics in 2018. They ruled out any leakage of gravitational waves into extra dimensions at cosmological scales for models involving more than 4 spacetime dimensions, constraining the crossover scale to greater than approximately 0.4 gigaparsecs, a distance far larger than any structure a leakage effect could plausibly hide behind. Model builders proposed that gravitational waves and gravitons leak differently. No framework produced this splitting cleanly. They proposed the leakage was direction-dependent. Subsequent LIGO detections from different sky locations returned the same null. They proposed the leakage happened only above a certain frequency. That frequency was then pushed above LIGO's sensitivity range, making the claim untestable. They proposed the effect averaged out over long distances. LIGO's precision is now good enough to see effects that would not average out. A ripple in the fabric of spacetime, generated by two black holes crashing into each other 1.3 billion light-years away, arrived at a detector in Louisiana at exactly the amplitude that a universe with 3 spatial dimensions predicts. If extra dimensions exist, gravity is not draining into them at any scale a human detector can see. What is the largest thing hidden in our universe that we will never observe because our best instrument is telling us it is not there? Even the LHC's most precise energy accounting has produced the same silence. Number 3. The LHC's missing energy search. Nima Arcani-Hammond, Savas Dimopoulos, and Gia Diwali were not fringe theorists. In 1998, working at Stanford, they published a paper in Physics Letters B titled The Hierarchy Problem and New Dimensions at a Millimeter. Their proposal was radical. The extra dimensions everyone had been searching for at Planck scale energies might in fact be as large as a fraction of a millimeter. If those large extra dimensions exist, particle collisions at the Large Hadron Collider should occasionally launch gravitons, or other particles, into them. Because the graviton carries momentum and energy, but never re-enters our three-dimensional slice, the detector should register collisions in which measurable energy simply vanishes. Missing energy, momentum imbalance, a silent leak in every event. The ATLAS and CMS collaborations have been searching for these signatures for over 15 years. The energy balances, nothing is missing, the books close. In a monojet analysis published in the Journal of High Energy Physics in 2021, ATLAS ruled out large extra dimensions with fundamental Planck scales below approximately 5 to 12 teri-electron-volts, depending on the number of extra dimensions assumed. CMS reported comparable bounds in Physical Review D the same year. The parameter space in which the model solves the hierarchy problem is now almost entirely closed. Theorists said the graviton production cross-section was lower than predicted. Refined calculations kept the cross-section within reach, and still nothing appeared. They said the extra dimensions were smaller than the original proposal, that shifted the model into a regime where it no longer solved the hierarchy problem. They said the leaked particles were re-entering the detector as photons. Dedicated diphoton searches also came up empty. They said only certain quantum numbers coupled to the extra dimensions. Every quantum number-specific search has returned null. The largest scientific instrument ever built by humans, sitting under the border between France and Switzerland, has watched over 10 quadrillion proton-proton collisions. No energy has ever vanished into a hidden dimension. If those dimensions exist at any scale the LHC can probe, they are locked shut against us. How many collisions do you record before the absence of a signal becomes a signal in itself? The most spectacular version of the missing energy search had a target far stranger than gravitons. Number 2. The LHC's search for microscopic black holes. The same 1998 Arcani-Pym-Dimopoulos-Diwali proposal contained a second, more startling prediction. If extra dimensions are large enough to bring the fundamental scale of gravity down to LHC accessible energies, then proton-proton collisions at the LHC should occasionally form microscopic black holes, tiny, unstable, evaporating almost instantly through Hawking radiation into a spray of standard model particles. The papers laying out the phenomenology followed within 2 years. The predicted signature was clean and characteristic: high multiplicity events with roughly democratic decays into quarks, leptons, and photons, spherical energy distributions, total invariant masses near the threshold where the black hole would have formed. The models even predicted the production rate. For the parameters that solved the hierarchy problem, the LHC should have been manufacturing black holes at rates measured in events per hour, 0, not 1 candidate. The collider ran, the detectors watched, the theorists waited. Nothing has ever been produced that matches the signature. CMS, in a search published in the Journal of High Energy Physics in 2018, excluded sigma-analytical black holes with masses below approximately 6.2 to 10.1 teri-electron volts, depending on the model assumptions. ATLAS reached compatible constraints in physics letters B the same year. The parameter space large extra dimension models required has been almost entirely closed. Theorists said the black holes were quantum, not sequential, and decayed differently. Dedicated quantum black hole searches also found nothing. They said the black holes formed but immediately re-entered the extra dimensions. This made the model unfalsifiable. They said the production cross-section was suppressed by unknown quantum gravity effects. This admitted, effectively, that the theory could not predict what it had originally been designed to predict. Each rescue further hollowed the theory it was meant to save. We built a machine explicitly capable of manufacturing black holes if a specific class of extra-dimensional theories was correct. That machine has run for over a decade. The black holes did not appear. The universe declined to be that generous. What do you conclude when the machine you built to test a theory works perfectly, and the theory produces nothing? The oldest and most patient version of the search happens on a table smaller than a desk. Number 1. The Eöt-Wash torsion balance tests. Eric Adelberger, a nuclear physicist at the University of Washington, was not looking for extra dimensions when he started the Eöt-Wash group in the 1980s. He was testing Einstein's equivalence principle, the idea that gravitational and inertial mass are exactly equivalent, using a torsion balance descended from the early 20th century instrument built by the Hungarian physicist Loránd Eöt-Wash. Extra-dimensional physics arrived on his doorstep in the late 1990s, when theorists realized his apparatus was the most sensitive test of short-range gravity ever built. Newton's inverse square law states that the gravitational attraction between two masses falls off as 1 over the distance squared. If large extra dimensions exist, that law should break down at distances comparable to the size of those dimensions. Gravity should become measurably stronger than Newton predicted at short scales. The torsion balance should twist more than expected. For over 2 decades, the balance has twisted by exactly the amount Newton's inverse square law predicts, to parts in tens of thousands, down to distances smaller than the thickness of a human hair. The most recent published constraints from the Eöt-Wash group in a Physical Review Letters paper in 2020 by Lee, Adelberger, Cook, Fleischer, and Heckel extended the inverse square law's confirmed validity down to length scales of approximately 52 micrometers, with subsequent analyses pushing that boundary further toward roughly 40 micrometers. Every improvement in sensitivity has produced the same result: no deviation, no signal, no departure from Newton. Theorists said the extra dimensions were smaller than the balance could resolve. Every improvement in sensitivity has been met by the same silent result. They said gravity did not propagate into the extra dimensions the way the model predicted, but that removed the model's original motivation. They said the deviations were oscillatory and averaged to 0. The Eöt-Wash team designed geometries that would break the averaging. They said the dimensions coupled only to certain matter species. Mass composition tests found no such coupling. They said the effect was masked by systematics. The systematics have been controlled to a level below any predicted effect. A pendulum roughly the size of a soda can, spinning in a laboratory in Seattle, has spent longer than most graduate students' entire lives failing to detect any hint that the universe has more spatial dimensions than the 3 you are moving through. If they are there, They are hiding in a space thinner than a strand of hair. How many decades does the same null result have to accumulate before you accept that the answer is not hidden? It is simply no. Every experiment on this list was designed to detect something specific. Each one produced a null result. The universe is not confused about how many dimensions it has. We are. The theories predicting extra dimensions were built by some of the most rigorous minds in 20th century physics, tested by the most sensitive instruments ever constructed, and returned nothing but silence. That silence, at some point, stops being an absence and starts being an answer. Whether we are willing to accept the answer is a different question entirely. If you want to see more videos like this, click the video on screen now.